What's up, man? Hey, do you guys have an ETA on the videos?
Well,
Just
we
so I
got
can give my
an
heads up.
email back from Katz
Yeah.
about the iTunes U stuff. I
Okay.
guess there's some issues. We have to cut out, like, when you do roll call and stuff like that. That's the
FERPA.
Since it's not going to be, since
Yep.
it's not internal anymore.
Yep.
So we got to do that this week. So that's kind
What about the raw dumps just to the pilot page? Are you still planning to do that,
Yeah,
or
we
was
can do
that?
We could do that.
If you would do that, just so that the class here can be able to watch the lectures.
Okay.
Like in general, if you can't turn it down in one day from Tuesday to Thursday, that's okay. But if we could try and get them both up before the weekend so that people can go back and watch it.
Definitely.
Is that cool?
Yeah, that's definitely. So
Okay.
yeah, there's just a little bit of a backup that we're getting because of the iTunes U stuff.
Okay, but as far
we
as
can
just
get it
taking
up
the
now.
raw footage or whatever, yeah, if you would add that to here, and then I'll let them know it'll go up there. So if that's easy to do, and you can get that up, that way when people miss a lecture or whatever too, they can just go to and that one can have the roll call or whatever, right? If it's
Right,
internal,
yeah,
it doesn't matter.
Yeah, that's
okay, yeah, polishing out the ITU stuff, I'm fine with that. Whatever you guys need to have it kind of out there.
Okay. Sounds
So
good.
okay, just keep me posted. You got the sound good?
Yeah.
Okay. Hello, please grab one, pass it along. Attendance sheet is going around. All right, just recapping from last time. Homework number 1, MATLAB homework number 1 were posted last week. Okay, and you guys can download that stuff under the content browser over here. So if you look on homework, this is where it will go. MATLAB homework 1, homework 1. Again, the handwritten homework is homework that comes out of this textbook. Right, and the MATLAB homework is homework that comes out of this textbook. Okay, and you guys should be doing things in recitation this week that relates to these homeworks. These homeworks are due at the end of the week, right, by 5 o'clock p.m. on Friday. You can turn your homework in early if you want to do that. Dropbox is in the basement outside O26. I assume the TA's names are all up on the Dropbox. Anybody get a look at that yet? Possibly. Let me know if your TA's name is not on the Dropbox. Okay, we'll get that sorted out. But you should be able to wrap it up at your convenience. We understand not everybody's on campus on Friday. Okay, and so as you're doing the homework, again, work in groups. Do not copy each other's work. When you have questions, ask your peers. If it's not clear what's going on, you want a different explanation besides mine, go to the help room. Everybody know where the help room is?
Basement?
Nope. It is in the Student Success Center. Okay, we actually had used to be, you had to walk in the main doors of the Success Center to get back there. It's the back room. We actually knocked a hole in the wall and put our own separate door entry to the back. So the door number is 280H Joshi, right off the Joshi atrium. So when you're looking at the Success Center, just make a left about, I don't know, 50 feet down the hall on your right will be a glass door you can see right inside it. That's the help room. There should be TAs available between 8 a.m. and 8 p.m. There should be somebody in there all the time. Sometimes as many as 3 different TAs available. Okay, so again, this is a class where we expect a lot out of you. You got to go to lecture twice a week. You got to go to lab, recitation. You got written homework, MATLAB homework, labs due. We get it. It's a lot of work. Okay, but at the same time, we provide what we like to think of as overwhelming support. Okay, and so you add up all the office hours across the 13 different TAs and 4 instructors. I'm not sure I even did that exercise, but it's got to be 80 plus hours a week. Somebody is around to help you. Okay, and so just go. Make use of the resource. If you don't understand, do what you need to do until you understand. Okay? So that's where we are with that. Another note, we are videotaping lectures. We're kind of getting new at this. We're going to put it out on iTunes U. You can see how you can get to that right here. Okay, and so we'll have a version of what I do in here available for the whole world to see, but at the same time, separately from that, we should have, okay, if we go back here, let's see, there's going to be a place for distance learning videos that will show up right here. Okay, and so they've been dealing with some things like, you know, when I read your names and such, we can't have that out on iTunes U. It's a privacy issue. So they're going to do some editing and things of the videos for that. But what I just talked to the distance guy that was just in here, and what I'm doing in real time here, whether I read your names or not or whatever, we can put that internal to Pilot, just a raw video dump. So my goal would be to just get that done after every lecture. That way, if you have an excused absence, okay, or if you want the 1% hit on your course grade and you have an unexcused absence, at least you've got the material out there and you can go back and watch it. Okay, so we'll have that available if you like the resource. Okay, and then the other thing besides that I will point out is a reminder that everything I do in here, like today, the handout we just passed out is posted. There it is if you lose it. Okay, everything that I do, every problem on the board, the lecture notes, these are the actual handwritten lecture notes. It's the same thing I have in my hand when I am in here. Okay, so there's none of this like I'm hiding what I've got and you got to try and keep up. Again, my recommendation is have a blank piece of paper, do the problems with me in real time. I'll try and keep you engaged as much as we can. But always download the posted stuff. It's our original course content. You can have a whole separate binder of just our stuff. Okay, and then finally, some students prefer to just have it with them and make notes on top of it. Again, I'm not going to tell you how to learn, but the resources are there for however you want to use it. Any questions before we move forward? Yes?
Is there recitation in that?
There is recitation, yes, per the regular schedule. So, you know, Monday, if there was a Monday recitation, somebody have the staff list? Do we have a Monday recitation? We had a Monday lab. We try and stay away from Mondays because there's missed days and such. So I already commented, if you have Monday lab, you're going to be a lab out of sync all the way until Thanksgiving week, and then you'll get caught up. Okay, if you didn't have Monday lab, you'll be starting lab 1 this week. Everybody's got recitation, yeah, this week, Tuesday, Wednesday, Thursday recitations. Other questions? Everybody know where Hamilton Hall is? This is where recitation is, right? Right by the student union. You walk out right where the food is, right across the hall. Your swipe card works for the south stairwell. So when you get into Hamilton Hall, if you try and go down the wrong door, you'll think you don't have, you know, swipe card access. So just ask somebody which one of these is a south stairwell. Okay, that's the one that it works. And there's usually somebody in that front office there in Hamilton Hall also. Okay, so you'll work out the kinks, but make sure you can find your way down to the basement. Anybody here live in Hamilton Hall? Not that many. So if you do, I mean, one of the reasons we took over, you know, a room in a dorm is there's an added convenience there for you. Feel free to throw in your laundry and go to recitation. That's the idea. Okay. Everybody know where the lab is? Lab is in the basement of this building, O26 Russ. You just take the nearest stairwell down the hall, down one flight, around a corner. There it is. Same place you turn in the homework. All right, so we know where the help room is. We know where the lab is. We know where the recitations are. Are we good? You know where the dean's office is? 4th floor upstairs. I don't have a ton of office hours. Okay, happy to talk to you anytime you can pop by and see me. I do have regularly scheduled office hours, 1 hour before class each week. Okay, every now and then I'll get the provost or some other deans or something that require my time at that time. If that happens, I will try and make up the office hours. Okay, in fact, I'm looking at my schedule and that might happen Thursday. So if it does, I'll send out an email to this class and I'll let you know when you're going to get your hour. Okay, probably immediately after class is usually a good time for me also. Okay, that also means like when I'm leaving here. If you have a question, clarification, course material, something you don't understand, right after class, good time to grab me. All right, so we are moving on. So one other thing I guess I'll comment on is, you know, so last class, the last couple classes, we did not get through all that was posted in the lecture notes, and I understand that. So it's also why we post all the notes, so I can say, well, it's out there, have a look. The lecture notes are the content for the textbook. The textbook has additional information, but there's nothing in the lecture notes that's not also in the textbook. Okay? And so the key thing is when you're trying to figure out, boy, well, he didn't get through everything here. We will assign comprehensive enough homework so that if you're comfortable with all the homework and then we post prior exams and everything, you'll know that you're ready to go. At the same time, the lecture notes have multiple worked examples all the way through. Okay? Depending upon the topic that we're on, sometimes I need to get through almost all the examples in order to hit what I think are the learning objectives of the topic. Quadratic equations, it's can I do it by factoring, completing the square quadratic formula. I get through that learning objective in one example. That's all we had time for in week one. Week one is compressed. We got to talk about course policies, all the rest of that stuff. Okay, moving forward, we'll try and get through as much as possible, but I won't get every detail of what's in these trigonometry lecture notes up on the board. Okay, I will focus on keeping a pace where I can keep everybody engaged and not lose the average student behind me. Okay, and I will make sure we cover everything I think is a critical part of the learning objective. All right, so bottom line is just listen for me to say, if I don't get to an example, I might reference the notes and say, hey, there's another good one that talks about this. Please have a look at the notes. Again, it's the reason we post them. Okay. Anything else before we move forward? All right, so we're moving on in trigonometry. Now we got 1 week to do trigonometry. So I would argue that I can cover all of kind of the critical background of trigonometry in 2 80-minute lectures. Okay, and I already burned 10 minutes of the first part. Okay, and so here's the thing. There's more to trigonometry than this. Okay, there could be some students in here right now registered for trigonometry, and that's great. Okay, but what we're trying to do is set it in the context of the way we're going to use it here in this building in kind of a physical context. We'll do that in the laboratory as well next week. Okay, and it really sets us up for the next couple topics, which are things like vectors, complex numbers, sinusoids and signals. It's all based on trigonometry. So trigonometry in engineering, it's kind of like algebra. It's the language with which we solve problems. Okay? And so the assumption is, if you're in this class, that you've had some trigonometry before. We're not presenting it as though you've never seen it. We're presenting it as though here's a quick and dirty review of trigonometry, but set in context that will be helpful to your understanding. Okay, so that's the idea moving forward. If your trigonometry skills are really great, this will be a breeze for you. If they're kind of rusty, you'll appreciate it. If they're pretty bad, you'll have to work hard in the next week or two to get on track. Okay, and so you'll have to make a decision about where you are in that continuum. All right, so trigonometry in engineering. The topic that we use for this is what we call a one-link robot. Okay, so this is the one-link robot. And the corollary to this is the two-link robot that we won't get to today, but that'll be next week. Okay, and so what do we mean by a one-link robot? Well, essentially, a robot of any type, okay, typically a mechanical robot, right, will have some links that are controlled by motors. Okay, so if I want to think about the robot here, and what this really is basically a plane here that's got feet on it. Okay, and what I'm going to do is put a coordinate axis right in the middle. Okay, and so let's say my coordinate axes are labeled y and x, just like you would in a math book. Okay, then if I have a one-link robot, then right at the center, okay, I will have a motor which will control the motion of a link. Okay, so there's my motor right there. Okay, and the link is just a bar that is going to rotate around in the xy plane. Okay, and so I'm going to locate the end of the link, okay, with another dot there, and this point will have coordinates x and y. So I'm going to call the end of this guy point P, and the coordinates will just be x and y, just like points in an xy plane. Okay, and so here it is. So in order to denote the geometry of this link, okay, I need two things. I need to know how long is it, and we're going to use L as the length of the link. Okay, and then I need to know where is it located physically in terms of the orientation in the xy plane. Okay, and that's this guy here, which is the angle theta. Okay, and so what I want to talk a little bit about is, given those values, L and theta, right, because it's my robot, so I know how long the link is because I designed it. And then the argument is, in order to sweep out the positions that I might have here, I can control the angle theta because I control over here the motor. Okay, so that's it, right? And again, of course, this guy is the link. All right, so here's the question. Given L and theta, okay, what I would like to find is the coordinates, okay, of point P. Point P, which is sitting at an XY location. Okay, that's the idea. So first of all, what are all the points that lie on the tip of this robot? Okay. What do they all have in common?
Same hypotenuse.
Same hypotenuse. What's a hypotenuse?
A squared plus b squared is the hypotenuse squared. So
All right, so relate that to this picture here.
So the value of the x.
I'm sorry, can you repeat that?
So the value of the x squared plus the value of the y squared is always going to equal the same value.
Okay, so geometrically speaking, can somebody simplify that for me?
L is the hypotenuse.
L is the hypotenuse. Go ahead.
They're all an equal distance away from the motor.
Okay, so if they're all an equal distance away from the motor, then as this thing spins, it makes what kind of shape? A circle. Okay, so that's one thing, right? So all of these guys lie on the same circle. Okay, so all points, they lie on a circle. Okay, with radius what? Yeah, with radius L. Okay, so that's the first thing to understand. This thing sweeps out a circle. Okay, and so let's talk a little bit about how we can characterize, the value of the angle itself. So here's y and x again. Okay, and this thing, right, here's the tip. Okay, as I rotate this thing around, okay, in the xy plane, okay, then the idea would be that if this is point P, then the two coordinates are x, which is the distance from the y-axis, and y, which is the distance from the x-axis. Okay, and here's L. Okay, and so as this thing rotates around, okay, it will sweep out a circle, right, in the xy plane. Okay, something like this. All right, so there it goes. As it sweeps out the circle, okay, I am moving the angle theta. So positive theta, all right, is as shown from the x-axis towards y. Okay, and likewise, I could go the other way, right, if I reverse the motor, and I'll have negative theta. Okay, so first of all, let's talk about basic definitions of theta. Okay, what is the range of a positive theta? 180 degrees. Okay, so I can think about that as 0 less than or equal to theta less than or equal to 180 degrees. Is there any other measure of angle besides degrees? Radians. Okay, so who knows how do these numbers convert over to radians? So 0 is still 0, right? So I'll say or 0 less than or equal to theta less than or equal to how many? Pi. We'll talk more about that in a second. Okay, so in radians, that would be it. Okay, and then of course I can have negative theta, which means I'm just going the other way with the motor. Okay, and if I have negative theta, then the ranges are what? So it's just the other side of this, right? So if it is the smallest number, then it would start at 180. But if I want to leave a 0 here, then I would say 0 is greater than or equal to theta, which is greater than or equal to negative 180 degrees. Okay, and I can make the same argument in radians. So or theta, or 0 is greater than or equal to theta, greater than or equal to negative pi radians. Okay. So according to this, right, how many degrees is a radian? So pi radians is how much? 180 degrees. Okay. So before I move forward, hey, I got to make a couple of points. Hey, number one, in engineering, we will use degrees and we will use radians depending upon the context, depending upon the application. Okay? But as a student, all right, you really got to have a good sense for which one of these things has any kind of physical meaning. Okay? So let me throw this out there. I got two measures of angle. I got degrees and I've got radians. I would argue that one is a physical result of geometry and the other one is made up. Okay? Made up. Arbitrary. Any ideas which is which?
Radians are a result of geometry.
Radians are a result of geometry. That's the suggestion. Okay? Which would then imply that degrees are made up. Okay? Now, it's arbitrary in the sense that, you know, if it were me, right, if this is 180 degrees, then how many degrees all the way around? 360. So that also means that if I go from here, right, to straight up and down, this is a right angle now. How many degrees is that? 90 degrees. So it's like, you know, it's born into our blood, right? We take geometry in whatever, 9th grade, and they teach us about, you know, right triangles and a right angle is 90 degrees, yada, yada. How many quadrants are there? 4. 1, 2, 3, 4. Okay, now, if it were me, and I was just arbitrarily making up degrees, okay, then, you know, why not 100, 200, 300, 400? Seems a lot easier than multiplying by 90, right? 90, 180, this one is 270, 360. Okay. All right, so there's historical significance, okay, about why we got numbers like 360. Anybody have a sense for that? Last time I asked this, somebody whipped out the smartphone and had it on Google or something. Yes?
It has to do with the number of days in a year in the sun, orbiting, or the Earth orbiting the sun.
Yeah, the guys that did these kind of things, right? Greek astronomers, philosophers, scientists, I mean, they were looking at the sun, they were talking about the Earth's rotation and the time and all of that, right? So there's reasons why 360 was chosen, okay? But it is an arbitrary thing, okay? And in fact, a unit of a degree, okay? That's a good question. I mean, physically, how big is a degree?
Should I use scientific notation or something?
Sure.
Never mind.
Never mind.
Yeah, with decimals, a degree or 1/360th is 0.0027 repeated.
So 0.027 repeated what?
Oops.
Feet? Miles?
This isn't making any sense to me either.
Okay.
All I did was take 1 divided by 360.
All right, let me ask you this one. Do you guys remember this? Again, this is a bit of an aside, but we've got to understand what's a physical quantity and what isn't, right? If I have a circle, because you just told me that these things all make a circle, right? So here's a circle. Does anybody remember the relationship between these three things? Here's theta, here's an arc length s, and there's the radius r.
Isn't it S equals R theta?
Yeah. S is equal to r times theta, right? Now, if I use that formula, what measurement is theta? Is this like 43 degrees? Can I put that in here to get the S?
No.
Yeah, this only works if theta is defined according to this definition. Okay? This is a physical definition, right? In other words, if theta is 1 radian, right? Theta is equal to S divided by R. The units on that is what we call a radian. If theta is equal to 1 radian, what does that mean geometrically? 1 radius.
If the radian equals if theta is equal to 1, the arc length and the radius are equal.
The arc length and the radius are equal. Right? I mean, so when I ask a question, you know, what is a radian? One answer is to convert that to degrees, and you get some answer. It's 50-something degrees, right? Why is that? Well, 1 radian, okay, is the angle such that if I take the radius of the circle, measure it out with a piece of string, I can then take the string, the exact same length that I just measured, and I can wrap it around until I hit the intersection point there. Right? So a radian is the measure of angle such that the arc length equals the radius. Okay. So we're trying to get to this, by the way. Okay. Why is pi radians 180 degrees? Okay. What if I have the circumference of the whole circle? So for example, if S is equal to the circumference, okay, what does the formula say about theta?
Theta equals 2 pi r over r.
Yeah, right. Theta is equal to 2 pi r, right? That's the circumference of a circle, no? This is geometry, right? So the geometry handout from last time. 2 pi r, it means if I took the radius, I would have to take 2 pi of them to wrap them around the outside. Right? What's the closest whole number to 2 pi? 6. Okay, so it's about 6 radii to get around a circle. That's true no matter how big the circle is, right? It is a law of geometry. You can put it on a piece of paper and you can measure it, right? You can build it with a string right in front of you. It's a piece of physics. So it's 2 pi r divided by r, which means theta equals 2 pi radians, right? So the fact that there's 2 pi radians all the way around a circle is a result of geometry. It's not made up. Is this clear? So the conversion factor comes when I say, well, you know, what's all the way around a circle in degrees? Yeah, which equals 360 degrees, right? And the conclusion is pi radians equals 180 degrees. Okay, so that's where the conversion factor comes from, right? But the thing I want you to understand is this guy here, 360, this is made up. Okay? If it were me, it would be 400. If I was born in ancient Greece, okay, then it wouldn't be. It'd be 360 because I'd be looking at the sun and the planets and all the rest of that. Okay, so it is a historically, arbitrarily chosen value, okay, that relates to astronomy and everything else. Okay, but really what it means is this little symbol right here in any engineering derivation, okay, that involves physical parameters and an angle. The measure of the angle has to be what? Has to be radians, right? And how do you know? Well, suppose I'm in the English system of units, right? Inches, feet, etc. Or maybe I'm in the SI system of units, which is meters, millimeters, centimeters. Then arc length would be measured in what? Meters. Radius is measured in what? Meters. Meters divided by meters is what? Nothing. Okay? So this guy right here, okay, is no dimension. Okay? That's the point. I asked you how big was a radian. A radian has no dimension. Okay? It is dimensionless. Right? It is one length divided by another length. That's it. So things that are dimensionless in engineering are dimensionless from a physical viewpoint. When I derive it from the physics, from the geometry, the units go away. Therefore, it's dimensionless. I can't arbitrarily come in and say I'm going to stick a degree symbol in here. Okay? Because this entire relationship, the ratio of these two things, stems from the fact that it takes 2 pi radii to get all the way around a circle. It's the law of geometry. Are you guys with me? So when in doubt, in an engineering classroom, okay, when you're doing a derivation, when you're thinking about physical parameters like the length of a beam or the stiffness of the material, and you get an answer for theta and it's got all these letters in it, it better be dimensionless. And when it's dimensionless, that means that the unit you write down is what? Radians. You guys with me? All right, now that being said, I give this big lecture on how radians is the right answer, yada, yada. In engineering, we use convention, right? In fact, the rest of the world uses almost predominantly SI all the time. Meters, seconds, all the time. In the United States, where a lot of engineering business gets done, when we talk about things like stresses and failure, we use English, PSI, pounds per square inch, okay? And so the thing is, we got to live with convention, and we use convention when we need to. So in this class, we'll jump back and forth between SI English units depending upon the context, the application, however we use it. And when we talk about angles, we'll use degrees all the time. Okay? And it's because you guys are born and raised in, in the US, but I mean, frankly, they do this everywhere else also, right? The historical significance of thinking about 90 degrees is a right angle, 360 is a circle. It's so far ingrained in our brains that we use that notation. So you need to be very sensitive about when I calculate something, am I using radians, am I using degrees, when do I need to convert, and also know what the buttons are on your calculator, right? Because your calculator can do things in either mode, right? They could be degree mode, radian mode, etc. So make sure, when in doubt, when you get a number that does not pass a sanity check, if there's trigonometry involved, you got to be thinking about, am I supposed to be in radians? Okay, because that's probably where you screwed up. Questions on this, degrees, radians business? All right, so given that we have a physical measure of angle, okay, what we want to think about is basic definitions that have to do with the XY system, right, and the triangle that we have here. We've already had people talking about it. Okay, so if I want to relate x and y to L and theta, okay, then you can always do that with a triangle. So x and y are related, okay, to L theta, okay, by what we'll call the reference triangle. Okay, and in fact, all of the trigonometric definitions come from basic triangle geometry. Okay, the difference is trigonometry extends that out into the entire plane, much like the motion of the robot. Okay, so here's y and here's x. Okay, and if I want to relate again, points at the end, this is point xy, to the length of the link, L, and the angle right here, theta. Okay, then I have to keep in mind that at angle theta can be anywhere between 0 and positive 180 degrees, negative 180 degrees, plus or minus pi. However I want to think about it, it could be in any of those 4 quadrants. So what we want to do is think of relationships between x, y, L, and theta that will allow us to control this robot and put the tip where we want it. So already somebody was talking about hypotenuse. What's the hypotenuse in that picture? All right, so there's 1, and I would calculate L how? Pythagorean theorem, okay, another basic law of geometry. Okay, you could sit down and you could measure this, right, by making a triangle on a piece of paper and measuring the lengths. And it is always true that L squared is x squared plus y squared, which means if I want the L for a given x and y, L is the square root of x squared plus y squared, and you guys already said that's called the hypotenuse. Okay, so that's 1. What about the basic trig functions? Who knows the definition of the cosine function?
Cosine of theta equals x over L.
Yeah, so cosine of theta, okay, is equal to x divided by L. If I were in geometry class, then I would say that's what? Adjacent over hypotenuse, right? So geometry, there's all these triangle definitions. What trigonometry does is it thinks about this thing rotating around and takes into account that the triangle shown here can be in any of these 4 quadrants. Okay, and so now what I get is really functions of any point here, as opposed to just a definition for a triangle. Okay, so it's a more general way to think about it. So that means if I were given the L and I were given the theta, how would I calculate x? Yeah, x is equal to L times the cosine of theta. Now, I purposely did something right here. Okay. On the left-hand side, I used functional notation, cosine of theta with parentheses. Over here, I just wrote it as cos theta with no parentheses. Okay. Anytime we use a trig function in engineering, and we have sine or cos and something right after it with no parentheses, it is understood that this is what we mean. Okay? The reason we do that all the time in engineering classrooms is we do a lot of calculations with sines and cosines and other functions all over the board, and it's just shorthand. So I want to make a distinction again. When you're in an engineering class, you'll see things done mathematically that you might not see in a math class. It's shorthand. Okay? And so sometimes I'll put a parentheses if I want to be crystal clear, if I think that it might not be clear from the context. Usually we won't. L cosine theta means the cosine of theta. You guys with me? Okay, very good. All right, so how about the sine of theta? Who knows what that is? That is the opposite over the hypotenuse. That's the geometry definition. So that would be the y divided by the L. Okay, and that would mean that if it's my robot and I know the L and I put the motor so that it's at a certain theta, then I can calculate where the y is going to be, and the y would be where? Yeah, it'd be L times the sine of theta. Okay, and I'll do it again. I'm going to leave the parentheses out. Here's a nice aside for you. Okay, when you take trigonometry class that most people in here have, okay, you do a lot of proofs of what's called trigonometric identities. We don't do a lot of proving things in here. We do a lot of using identities. If you look at the handout, they have fundamental identities, a whole bunch of them used. Let me take this opportunity to reiterate, this page is from your calculus book. Okay, so this is the trigonometry that the mathematicians that write calculus books say, if I could put everything that I really need from trig on one page, this is what I would put. Okay, so the upside to that is that it all fits on one page. Okay. All right, the downside to that is you could be working out an exam in Calc 3 a year from now, and they'll expect you to be able to pull some half-angle identity off the top of your head. Okay? Absolutely will expect that. It's really not unreasonable. Students always say, well, that's unreasonable. It's one page, guys. Okay, so as you progress through the math sequence, keep in mind, everything on here is important, or the mathematicians wouldn't have put it on one page. Okay, we'll use a subset of it heavily in this course, but not all of it. All right, and as you move forward in Calc 1, 2, 3, etc., you may use some of these things just out of the blue. They'll just assume that it's like adding and subtracting numbers. Okay, you ought to be able to pull the half-angle identity out. Okay, we'll do that occasionally in engineering as well. We'll feel a little more sorry for you when we do it. All right, so what if I take these guys, okay, and I square and I add both sides? So x squared, right, plus y squared. If I square this, what do I get? All right, so these are lined up, right? Think about if I squared both sides of the two equations and then I added them up in a row. On the left, I'd get x squared plus y squared. On the right, I would get what? I'd get L cosine theta, quantities squared, right? Plus I'd get L sine theta, quantities squared. Can I simplify the right-hand side? Can I factor anything out of there? L? Is it just an L? It's an L squared, right? Again, I could write the intermediate step. When I have a chance in here, I will do the most efficient algebra that I can do, okay? And I will explain to you what I did as required, okay? But this is L squared, and it's cosine theta squared. So if I take out an L squared, get you in just one sec, then what do I have left on the inside here? I've got a cosine theta squared, which we use this notation, cosine squared theta, right? It's an interesting notation that mathematicians even use, right? Not cosine of theta quantity squared, but cosine squared theta. That's what it means. It means the entire cosine squared, okay, plus sine squared theta, like that. Okay, before I move forward, we had a question. Question resolved. Are we good? Okay. All right, so apparently x squared plus y squared is equal to L squared times this business. But according to the first line, x squared plus y squared is supposed to be what? L squared. So then apparently this business is 1. Okay, and that is the most common of all trig identities. If you're a student, you remember 1. The fact that the sine squared plus the cosine squared is always 1, right? No matter what the angle is, that is an identity of trigonometry. Okay, the reason that that is true is because of the physical geometric relationship between the sides of a triangle right here that you can measure on a page. Right? And so as engineers, you should grow to love trigonometry because the entire thing is based on stuff I can make and measure myself. Right? And in fact, in Lab 2 next week, you're going to be doing nothing but that. Just messing around with different trigonometric relationships physically and measuring them out so you can get away from just believing stuff you can memorize, right, and actually observing what the physics is that drives the math. Okay? Questions about this? Yeah, so the idea is this is one thing times another thing to a power. So the power hits both of these, right? So it's L cosine theta times itself. I got the L twice, I got the cosine theta twice. So again, I skipped a step of algebra in between there. Again, whenever I can do that, I will. But happy to point out the details. Other questions? All right, so are there any other trig functions besides a sine and a cosine that you think we probably use in engineering and physics and in science in general? All right, tangent. What is the definition of tangent? How about the triangle definition, TAN of theta? It's the opposite over the adjacent, so it's y divided by x, right? So here's the beauty of this. If you understand the basic definition of a sine and cosine, every single thing on this piece of paper can be derived directly from that definition. That's it. Everything else is derivable. So it really is, it's just that. It is one triangle, it's an adjacent side and an opposite side, everything else is derived. Okay, and so if this is true, well, y, according to this, I already know what it is. All right, y is L sine theta. So I'll write L sine theta. And x is what? Yeah, the numerator is y. The denominator is x. That's L cosine theta. What happens to the L? Gone. All right, so apparently then, the tangent of theta is just the sine of theta divided by the cosine of theta. And that's true, you know, for any angle theta. It's a derived function. If I know the sine and the cosine, I've got the tangent. I don't need all three. All right, so we got that, right? Cosine, sine, tangent. What else? Who knows this one? Secant of theta. SEC. It's 1 over cosine just by definition. Okay, and so 1 over the cosine of theta. Okay, and how about the cosecant, CSC of theta? That is 1 over the sine of theta. Okay, and again, I'd have to, does anybody know the history of how that happened? Seemed like somebody really wanted to mess with their students, right? Because the secant is the cosine and the cosecant is the sine. Okay, just remember it's the opposite of the way you would do it yourself, right? That's the right answer. What else? Cotangent? Cotangent, right, of theta is equal to 1 over the tangent of theta. Okay, so you can see that every one of these things, if I have the sine and the cosine, I've got everything else. I just compute it from the sine and the cosine that I already have. Those are all the primary trig functions. All right, sine, cosine, tangent, secant, cosecant, cotangent. If you look at these fundamental identities. They're identities that all have those functions in them. Okay? Also shown is the graphs of all the key functions there as well, okay, where they are functions of, y a function of x. What are the units on the x-axis there? Radians. It's the angle, right? So they plot it right there in radians. Good. All right, so what I would like to do, okay, will seem to some kind of elementary. But I want you to think about, based on these basic definitions of trig, the things that we know, okay, having used trig before, and just take for granted, right? Things like the sine of pi is how much? 0. That's true. Okay? Some of these basic definitions, right, are things that you can observe by rotating the link and essentially concluding it by inspection. Okay? They're not things to be memorized. They're things to observe because it's physically based. Right? And so let's do that for some very trivial cases of angles. How do these definitions of sine and cosine, recover the physics that I can see by rotating the robot? Okay? So essentially what I'd like to do is let's find x and y, cosine theta and sine theta. Okay? And we'll do it for a few cases. So let's find x, y, cosine theta, sine theta, okay, given that somebody tells me the L and somebody tells me the angle. Okay, so the L can be any number, right? It could be a 5-inch long radius, right? This guy here maybe 8 inches, okay? Or it could be any length at all, which we'll just call L. That makes it more general. But the theta, I'm going to have to put an orientation here so I can inspect what this is. So the most trivial case, theta equals 0 degrees, which is how many radians? 0 radians, okay? If I am at theta equals 0 degrees, then think about, in the xy plane, where does that put the link? Somebody want to give me a explanation in words? Where's that link? Laying on the x-axis. So the motor's right here, okay, and the link is over here, okay, and this is it. Okay, now, I know how long the link is. L. Okay, I'm trying to find the coordinates, a point P at the end here. It's got x, y for the coordinates. Do I need to know the values of trig functions in order to write down the coordinates of this link? Not really, because I can do this by inspection, right? So let's look at this by inspection, right? X, y, the coordinates are what? Yeah, x is the distance from the y-axis. That's the length of the link, L. Y is the distance from the x-axis, which is 0. All right, so what about the formulas? I still have the formulas on the right side over there, right? What's the angle? 0, right? So I could try the formulas. X is supposed to be L times the cosine of 0 degrees, which by inspection is equal to what? L. Okay, this is the derivation of why the cosine of 0 is equal to what number? Yeah, it's equal to L divided by L, which is 1. It doesn't matter how long the link is, right? The cosine of 0 degrees is 1. I could do the same thing with sine, right? Because y is equal to L times the sine of 0 degrees. And by inspection, I can see what that is. It's 0. So according to this, this means that the sine of 0 degrees is how much? 0, right? So two very basic ideas, right? That the cosine of 0 is 1, the sine of 0 is 0. Those are results of the basic physics. All right, how about do another couple cases. How about 180 degrees? Okay, does it matter whether it's plus 180 or minus 180? No? So plus or minus, which is the same as theta is plus or minus pi radians, right? So where is this guy located in the xy plane? So it's on the other side, right? Other side. Okay, and so if I draw this location, okay, then the link is now laying on the negative half of the x-axis, right? And it's pretty clear from the picture, right, that this angle is theta equals, right, 180 degrees. Okay, or I could go the other way, right, and this is theta equals minus 180 degrees. Okay, and either one of those angles puts me at the same point. Okay, and here's my point P, x, y. So, by inspection, okay, can I write down the xy coordinates of the tip of the robot? Help me out. Yeah, x is a negative number, right? I don't see any negative numbers written down there, but clearly I'm on the left side of the axis here, right? So this L is the length. The hypotenuse is always a positive number, right? It's an absolute value. Where it ends up is on the left side, it's negative. Minus L. How about the y value? 0. Okay. So, if that's what it physically is, then this ought to tell me the values of the sine and cosine of plus or minus 180. Right? So this means, okay, that x is supposed to be equal to L times the cosine, I'll put the parentheses here, plus or minus 180 degrees, either one. Okay, and according to that, this is minus L. Right, according to inspection. So therefore, the cosine, okay, of plus or minus 180 degrees is equal to what? Yeah, minus 1. So already, I can see that the cosine can go anywhere from what two values? I can be all the way on this side, which is a positive 1. I can be all the way on this side, which is a negative 1. What about the y value? Y is supposed to be L times the sine now of plus or minus 180 degrees. Okay, and by inspection, that y value is what? 0. So apparently the sine of plus or minus 180 degrees is 0. Okay, something again that if you've had trigonometry, you just kind of memorize. All right, so according to this, then that means the sine can go anywhere between what? 0 and 0? Is the sine a boring function that's always 0? Probably not. We should maybe look at a case where the sine is not 0. And so for example, what if I look at theta is minus pi over 2 radians. Where's that? In degrees, that's how much? Yeah, this is minus 90 degrees. I like that one too. It's also, okay, or theta equals 270 degrees. Okay, I can think about this a gazillion different ways. Okay. In fact, how many different angles can I use to identify that location? Infinite. I can keep adding what number to it? 360, right? And so clearly these trig functions are not, right, different for all values of theta. They repeat, right? They repeat every time I get back around the circle, right? And that's called what kind of function? Functions that repeat every so often are called, well, sinusoidal. The sine function is sinusoidal. What do we call that in general? Periodic. All right, periodic functions. We're going to talk a lot more about that. We got a whole section on, harmonic signals. That's basically what we mean, the periodicity of sine and cosine functions and how we use that in engineering. Okay, here, just making that observation that clearly I can get back to that location a number of ways. So let's go ahead and draw this. So again, here's y, here's x, and if I am at negative 90 degrees, okay, then I am where in the xy plane? Straight down on the y-axis, like this. Okay, so here's the link, right? Here's the L. This is the point I'm trying to identify, right? And I can go ahead and draw this here like that. This is minus 90 degrees. Okay. All right, so can we do this again by inspection? By inspection, the xy location of this guy is what? So the x-coordinate's on the y-axis, so I got 0. Y-coordinate, negative L, minus L. Great. All right, so what about the formulas over here? So I ought to be able to try that. X is supposed to be equal to L times the cosine of minus 90 degrees. By inspection, x is how much? 0. Okay, and so apparently then the cosine of minus 90 degrees is 0. Incidentally, what if I was plus 90 degrees? Same problem, right? There's a pattern here, right? It's not just the formulas, right? But the cosine is what side of the triangle? This is x, this is y. X is the cosine, right? L cosine. Y is the sine. So the cosine is the horizontal leg. The sine is the vertical leg. When I don't have a horizontal leg, then the leg is how long? Zero, right? Okay. All right, so cosine of minus 90 is 0. And how about y? Y is equal to L times the sine, okay, of negative 90 degrees. Okay, and according to the inspection here, this is minus L. So this means that the sine of minus 90 is how much? Yeah, is negative 1. How does that compare to the sine of positive 90? It's a negative times the sine of positive 90, right? Great. So according to this then, it seems like the sine will also be bounded between what two numbers? Plus or minus 1. Okay. What about in between? We can look at any points in between. We'll stick one in between. What if I look at 135 degrees? Where the heck is 135 degrees? How many radians is that? It's 3/4 of the way, right? So this is 3 pi divided by 4 radians. Okay. What does it look like there? Well, let's put the location. Here's y, here's x. It's 3/4 of the way. Okay, and so I've got 4 quadrants here. 1, 2, 3, 4. Which quadrant am I in? Second one. This is number 2. Okay, and I'm 3/4 away from the first one, which means about where am I in that second quadrant? I'm halfway, right? I'm splitting the difference right down the middle. If I split the difference right down the middle there, right, then, clearly this guy is the theta. Theta is 135 degrees right there. I'm trying to find the location xy at the end, right? And keep in mind, y is this vertical leg right here. X is this horizontal leg right there. This guy is what we call the reference angle. All right, so the actual angle theta is 135. And there's an infinite number of ways to specify that. I can go around, around, around and get back. No matter how many ways I specify this location, I always make what angle right here? 45 degrees, right? So this little reference angle never has a sign, S-I-G-N, associated with it, right? It's just like a triangle. It is the angle inside that triangle, no plus or minus, right? All right, so great. So this reference angle really determines the geometry here. But then I got to keep in mind that, you know, it's in the 4 quadrants. So x and y can have a sign, S-I-G-N, associated with them based on where this thing is physically sitting. Okay, so if I just understand my values of sines and cosines for various reference angles, I can get the value of the trig function, in this case the sine and cosine of 135, by taking a look where it is. That gives me the SIGN. And then knowing the answer for some common reference angles, which is the kind of thing they made you memorize a lot of, I think, in high school trig class. All right, so first of all, is this one that I can do like literally by inspection without having memorized anything from geometry or whatever? Not really. Sort of, if you say, well, it splits half the difference here. So if I drew this to scale, which it doesn't look like I did, that x and y would have to be how? The same number. So if you call this one x and you also call that one x, and then you apply the Pythagorean theorem, there's only one answer for x. Okay, and you could actually do this by a little bit of math and some inspection. Okay, but that being said, if this was 43 degrees, if this was 37 degrees as a reference angle, I don't have it memorized. Okay, so some typical angles, we design engineering structures and things that have typical angles many times, and so it's useful to have some of these known. So for example, how would I do this? If I want to apply the formula, x is L cosine theta, right? Then x is L times the cosine of 135 degrees. Is 135 degrees one of the common angles that you just memorize? No, they're all acute angles, right? Between 0 and 90. Okay, and we'll get to these in a minute, but we're talking about numbers like 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees. So is there a way by looking at this that I can rewrite this so I'm using 45 instead of 135? Well, so I know that this reference angle is 45, right? Do I know what the sign, SIGN, of the answer is going to be here for x? It's going to be a negative number. So can't I just say, right, that by inspection, this is the inspection part, right, that x is actually a negative number. That's by inspection. And isn't it L times the cosine of the reference angle, 45 degrees? Okay. Are those not the same two statements? So there is some inspection going on here when you're not in the first quadrant. Well, then you have to look at this and say, well, no, I'm using the reference angle. Okay, so I can do any quadrant I want if I use inspection to think about the sign, SIGN, and I use the reference angle to do the math. All right, so I put the appropriate sign, negative, and now I got this. So cosine of 45 is one I would argue most high school students have had to memorize that at some point. Anybody know? One more time. Root 2 divided by 2. Okay, so minus L root 2 divided by 2. Now, just to be clear, the reason why this is done this way, right, is that if I have a special triangle where the angles are 45 degrees, right, 45 degrees, 45 degrees, it's a right angle, okay, then the relationship between the sides is 1, 1, root 2, right? Okay, and you can get that from Pythagorean theorem, right? 1 squared plus 1 squared is 2. Root 2 squared is 2. 2 equals 2. We're golden, right? Okay, so take a look at this. What's the cosine from a triangle definition? 1 divided by root 2, right? So I would just kind of ask you to think about this. What takes more ink to write down? L over root 2 or L root 2 divided by 2? This question has only one answer. What takes more ink to write down? You can account for all the ink, right? There's an L here, there's an L there. Here's a minus, there's a minus. Here's a root 2 here. Here's a division symbol, there's a division symbol. I still got this extra 2, right? There's more ink. Is minus L over root 2 wrong?
Well, it's not proper.
So why is it that I can't have a square root in the denominator? Somebody literally give me the exact reason why you can't have a square root in the denominator. Tell me the truth.
Because the square root isn't a whole number?
So if it's in the numerator, is it now a whole number? It's an irrational number, right? Root 2, there's an infinite number of digits, goes on forever. It's an irrational number. That's true. It's true whether it's in the numerator or the denominator. Why can you yourself not have a square root in the denominator? Yes.
What did he say?
He said because the math teacher told you not to.
Oh.
Okay, now look, ask your math prof, but I bet a professor for 14 years, and as far as I can tell, that's the only reason. Okay, I don't know. It's an exact number, L over root 2. I put root 2's in denominators all the time. Okay, now this comes with a warning. If your math prof says you can't put it in the denominator, then don't. Okay, it's an exercise in following instructions, but I'm just saying there's nothing wrong with the number. It's an exact number and it takes less ink. Okay, and in engineering we do so much calculation that the more you can streamline your algebra, the more you can streamline your parentheses, the more you can use less ink by putting a root 2 in the denominator, the happier you are. Okay, so I'm going to call this minus L over root 2. Good. How about y? What's the y value? L sine 135 degrees. Let's say I don't have 135 memorized, right, as a special reference angle. Can I rewrite that? So, first of all, is the y negative? This is the inspection part. I'm looking at it. The y is positive. Okay, so just to emphasize that, I'll even put a plus. Okay, so isn't L sine 35 really the same as plus L times the sine of just the reference angle, 45 degrees? And the sine of 45 is how much? Root 2 over 2, or? Yeah, plus L over root 2. Again, if you are so ingrained in the root 2 over 2 business, I'm fine with it. Okay, it's not wrong. It's just, it's your ink. Okay, it's your writer's cramp. All right, y equals plus L over root 2. Very good. Same as the x value, it is a positive number. Okay, so the point is, when you do trigonometry, right, you can use reference angles for special angles that you might have memorized. Other times, there's going to be numbers where it's just you need your calculator. That's most of the time in engineering. Yes?
I had a question.
Yeah.
How you went from negative L root 2 over 2 to negative L over root 2 in the same bottom. Like what was the step there that I'm not in this?
Well, so the way you get this is 1 over root 2. You multiply top and bottom by root 2, right? And so it's called rationalizing the denominator. They teach you to do this in high school math all the time. And it's all based on this idea that you can't have a root in the denominator, okay? You know, yeah, I mean, I don't know why that is, okay? It's just like, we had some examples in the notes last time, okay? When you work the quadratic formula and you get a negative underneath the square root. Okay, it is ingrained into your head in high school that therefore there's no answer. Okay? And as we'll see, we got an entire week in here called complex numbers. We love negatives under the square roots in this building. Okay, the entire field of electrical engineering, it's all negatives under square roots. Okay, and we don't use I's for that. We use what letter? Anybody know? We use J, and the reason we use a J instead of an I is because I is already used up. What do we use I for? Current. That's it. That decision's arbitrary, right? So we said, hey, let's use J. So the point is, all kinds of stuff you were taught in high school, if you get this, you throw out the answer. If you can't do this, you know, not always the case. Okay, and so your job as you fight through the curriculum here is to figure out, you know, which of the stuff is really, you know, arbitrary and which isn't. Okay, this is one of those arbitrary things. Okay, now honestly, there might be a rich historical reason or just a convention thing. Ask a mathematician, honestly. Mathematicians don't like square roots and denominator. That's absolutely true. I like them. All right, moving on. So, what we've shown, I think, is that we can use a reference angle and we can use some inspection to get the values of whatever trig function we want. And there's only so many quadrants you can be in. How many quadrants are there? 4. So really, trigonometry is pretty, you can wrap the whole thing into a nice little bow. Okay, and here's the bow for all of trigonometry, right here. Okay, is in general, okay, you got 4 possible quadrants. Okay, and again, this is assuming standard Cartesian XY system. Okay, then I've got quadrant number 1. We like to use Roman numerals for this. This is kind of arbitrary, yet standard. There's 1, 2, and then we got number 3 down here, and this guy's number 4. Okay, and what you can do is just by thinking about just this picture, if x, right, is the cosine, right, I'll even put it here. This is the cosine, and y over here is the sine. Then the sine, S-I-G-N, of the trig functions is just inspection. You could visualize the link in any one of these quadrants, and you could tell if it's plus or minus, right? Now, sometimes in high school, you'll memorize some acronyms. All students take calculus, or I heard some other. I don't see a reason to memorize stuff that you can just look at. It's right there. Draw the thing if you don't remember. Okay, but all it is this, right? So in quadrant 1, the sine and the cosine are what? They're both positive, right? So sine of theta is positive, cosine theta is positive. When I draw the triangle over here now, think about it. I move the robot to this quadrant. What about the sine of theta? Positive or negative? Positive. What about the cosine? Yeah, it's negative, right? If I move the link over here, clearly the x-coordinate's on the left side of the axis. Okay? Now, I keep moving the link. I'm down here now. Okay? And again, the y is the sine, the x is the cosine, right? So sine theta is what?
Negative.
Negative. Cosine theta?
Negative.
Negative. Okay? And finally, if I'm over here in the 4th quadrant, sine theta is the y value. Y value is negative. Cosine theta is the x value. Positive. It's on the right-hand side. Okay, so again, if you can remember an acronym for that, that's great. But I think it's not necessary. Just visualize the robot, right? Look at the x as the cosine, the y as the sine, and you can't get it wrong. All right, and then finally, if you're going to compute any of these by hand, and you know, the reason this is useful is, again, some basic types of structures that we like to have things kind of uniform, and we run into these special angles that if you know what it is, it's faster to do and you can get exact answers without decimals. Usually, I'm punching a calculator and I got some angle like 37.86 degrees or something, okay, and that's fine. But let me just summarize these. This is values for typical reference angles, right? So the argument is, I use the 4 quadrants to get the sine, S-I-G-N, right here. And then when I think about the value, it's just the triangle. I forget the signs, S-I-G-N, and I use just the triangle. So let's see if you guys remember what these guys are. So here's some reference angle. Okay, and we'll go ahead and we'll put the parentheses value over here in radians. Okay, so we'll put some common angles right here, and then underneath in radians. So we'll do 0 degrees, we'll do 30 degrees, we'll do 60 degrees, sorry, 45 in between. 45 degrees, 60 degrees, 90 degrees. And then underneath in radians, 0 is 0. How many radians is 30 degrees? Yeah, that's 1/6 of the way, right? So it's pi divided by 6. 45, pi over 4, 60 degrees, right? It's 1/3 of 180, so it's 1/3 of the way, pi over 3, and 90? Pi over 2, okay? So those are all the radians, okay? And so what I can do is I can write down the sine of theta and a cosine theta, and of course once I have those, I could write down whatever else I wanted, tangent, cotangent, secant, whatever. 0 degrees, okay? Now, when I ask these, just think about right here, reference angle just in the first quadrant, okay? Right there. Sine of 0 is what? 0. Sine of 30 degrees? Again, how do you know it's a half? You could measure it, okay? So when is the opposite exactly half of the hypotenuse? Okay, I could measure that. That angle is 30 degrees. Okay, so you could prove it, but basically you just got to remember it. Okay, how about 45 degrees? I'm going to write it like this, 1 over root 2. Okay, how about 60 degrees? 1 over root 6? Anybody? Corroboration on that? Root 3 divided by 2. How about 90 degrees? 1. Okay? By the way, you should have some sense of the numbers here, right? When you crank out engineering calculations, like what should these numbers? First of all, these numbers should all be bounded between what two values? 0 and 1 for reference angles. When I change quadrant, I might change a sign. So -1 and 1 is it, right? You do some kind of sign calculation, right? And you get some number that is 1.73. Probably screwed up, right? Okay, so how about the cosine? Cosine of 0 is what? 1. Cosine of 30? Root 3 over 2. There's a pattern here. Cosine of 45? 1 over root 2. Cosine of 60? A half. Cosine of 90? 0. What's the relationship between the first and second rows there? Why is that? What's going on there? Let me draw 30 degrees, okay? Sine of 30 degrees is how much? 1/2, right? 1, 2. Cosine of 30 is how much? Root 3 over 2. That means this side's root 3, right? You guys with me? You told me over here, right? So if the sine is a half, opposite's 1, hypotenuse is 2. If the cosine's root 3 over 2, and this is already 2, then this has to be root 3. Are you guys with me? All right, if this is 30, this is physics here, right? The reason this row goes one way and the other one goes, it's physics. This side is what? 60. Okay, and so the opposite to the 60 is the same as the adjacent to the 30 because we're talking about right triangles here. You guys with me? So relationships always between sines and cosines, even the functions, we'll talk about plotting the signals later, right? Things are just shifted over by a 90 degree, right? That's what they are. Okay, they're all part of the same triangle. So you really just need one row of numbers, okay? That's it. Everything else from trigonometry derived from this. We didn't get quite as far as I wanted, but I think we got some good understanding. Okay, so we will pick up where we left off. Same set of notes for next class.